Day to you. Hopefully, you're watching this on Monday or possibly Tuesday, I suppose. Um, for seniors, welcome to the last week of instruction of your secondary high school career. Um, we'll get started in this class by wrapping up parametric slash vectors. I'll try to keep it shorter than I did on Friday with that one. And just so you know, and we'll get there at the end of this, but we'll take a look at the context on a normal AP test back when this stuff was on the AP test, every year except for this one. So just a couple quick things. Parametrics and vectors are pretty much interchangeable as far as AP calculus goes. Uh, those of you who have been in physics or are in physics or wrapping up physics, or pre-calculus, you've dealt with vectors, and so you know that a vector gives you not just a numerical quantity, but it gives you, well, a magnitude and direction. Oh yeah. And so when I say that I have a position vector like I've got written here, it's not just a number, but it's probably an ordered pair that will be written, at least in this class, as an x coordinate and a y coordinate, and these zigzaggy brackets, they're actually called chevrons, um, are just what's used for a vector. So if this is a position vector, this part's going to be easy. The derivative of position is velocity, and the derivative of velocity is acceleration, but these are also vectors. And so we'll see in just a minute what a velocity vector looks like, an acceleration vector, but basically it gives you more than just a number. It also gives you a direction. And then this may be not as familiar to you, but the magnitude of the velocity vector is the speed. And speed is just a quantity, just a numerical value. So if I say that this is a position vector, my position is given by this ordered pair t squared t e to the t. And I ask you for the velocity, speed, and acceleration. This is actually fairly easy. The velocity is just the derivative of position, and there's no complicated, weird thing to go through. It's just simply the derivative of the x and the derivative of the y. And so this tells us in what direction it's moving. And then the acceleration is just the derivative of the velocity. So the derivative of 2t, the derivative of e to the t plus t e to the t. And I suppose I could combine those together and say that e to the t plus e to the t is 2e to the t, but I left it as is. And then the speed, the magnitude of the velocity vector. And so to find the magnitude of a vector, to remind you, especially those of you who haven't done this in a while, the magnitude of a vector like this is just the square root of the sum of the squares of the components. And so the x component squared plus the y component squared, and take the square root, and this is your speed. And so the example that I'd like to go through with you a little bit more thoroughly is this one. I have a particle that's moving along. Its position is given, well, at least its position at time equals 0 is given. It's at the position that's x coordinate is 1, the y coordinate is 2. The velocity at that moment in time is 3, 4, so it's heading up farther into the first quadrant. And the acceleration is not just given at a moment in time, but it's given as a function of time. So I've got the position at a certain time, the velocity at a certain time, and then the acceleration as a function of time. And that's a big distinction. And the 4 questions that I want to answer are: where is the particle at time equals 1? I know where it is at time equals 0. I want to know where it is at time equals 1. What is the particle's velocity and speed at time equals 1? And then finally, when is that speed minimized? So we'll start with some stuff that I'll need to do to get ready for these questions. Given the acceleration function, I'm going to work backwards and find velocity functions. And of course, to go from acceleration to velocity, I have to anti-differentiate. So the antiderivative of 5 is 5t plus some constant of integration. But I also need that the velocity at time equals 0 to be 3. So in the case of this one, 5 times 0 plus something equals 3. Of course, that value is 3. And then the antiderivative of 6t is 3t squared plus some constant. But at time equals 0, the value of the velocity needs to be 4. So I end up with this as my velocity vector. My velocity is a function of time as opposed to just at a specific value. And now that I have that, I'm going to be able to answer a lot of the questions. And actually, I'll maybe mention this. I'm guessing that if I gave this as a pop quiz today, first of all, that's kind of a jerk move for me to do on a Monday like that. But if I did, I would guess that a lot of people would say the velocity function could be anti-differentiated to give a position function. And I'm not going to argue and say that you're wrong, but I'm also going to encourage you to think of it like this. If I know where the particle is at a certain time, and I know how the particle is changing according to my velocity function, I'm going to use this and say that the location of the particle, at least the x component, is what the x component was at time equals 0 plus the integral of the rate that it's changing between 0 and 1. And so 5t plus 3, that's just the x component of the velocity function that we found back here, 5t plus 3. And so if I integrate that between 0 and 1, that'll tell me how much it changes. It was at an x-coordinate of 1, and I just plug this into my calculator, not like it's a really difficult antiderivative, but I don't know. I'm recording this on Friday afternoon, and outside it's beautiful, and so I just plugged it into my calculator and got a value of 6.5. And they do the same thing for the y value. I know that it was at 2, and then between 0 and 1, it changes according to the integral of the rate. And so I again plugged this into my calculator, and I found that it was, the y-coordinate was 7. So the answer to this question is, I forgot what it was. The x-coordinate is 6.5, and the y-coordinate is 7. So there we go. That's where it is at time equals 1. How fast is it moving in terms of velocity and speed? Well, I have a velocity function. My velocity vector looks like this, so I just plug 1 into that, and I get 8, 7. So again, if I'm looking at the x and y axes, at time equals 1, it was at, the location was 6.5, 7, so that's somewhere up here in the first quadrant. And then my velocity at that moment is 8, 7, which means it's heading in that direction. Well, maybe I need to slant that a little bit. The x component's a little bit bigger than the y component, so maybe it's something a little bit more like that. But it's at that point, and it's going in that direction, at least for that moment in time. The speed at time equals 1. Again, the speed is the magnitude of the velocity vector, which means I do this square root of the sum of the squares of the components. I found that the velocity was 8, 7, so 8 squared plus 7 squared, and then take the square root. I found it was about 10.63. So the speedometer on that particle reads about 10.6. But the velocity also tells us not just 10.6, but 10.6 going in that direction. The length of this vector is about 10.63. And then finally, when is the speed minimized? We're back to derivatives, except I'm taking the derivative of this speed function. The speed function is the square root of the sum of the squares of the components. So if the x component of my velocity is 5t plus 3, plug that in. Y component of the velocity, 3t squared plus 4, plug that in. This is a speed function. And so when is it minimized? This goes back to what we did way back in Unit 2 of this class. Well, Unit 2, Unit 3, back when we were doing applications of derivatives. We find where something has a minimum by taking the derivative and finding when it's equal to 0 and when it's changing from positive to negative. But for this one specifically, and I will again admit that the green grass outside is summoning me, so I just plugged this into my calculator and found that the derivative was always positive, at least when t was greater than 0. When t was less than 0, um, the derivative did switch to negative, but all I care about for a problem like this one is time greater than 0. I'm not going to go back in time. And so because the derivative of the speed is always positive, that means the speed is always increasing, which means its minimum happens at the smallest value for time at time equals 0. So there we go. I know that's a lot, but I also know that a lot of you have worked with vectors and velocities and speeds before. So hopefully that makes sense. If not, we'll have a chance to talk about it again tomorrow. But in the meantime, your homework assignment is actually this question from the AP test a few years ago, from 2016. I found this question actually, if we had done the vector and polar chapter in this class. This is a question that I have used as a test question in the past. So who knows if I would have used it this year, but today I'll just give this as a single question homework assignment. Try this one out before tomorrow, and we'll come back tomorrow and I'll explain what I did on this one. And let's see, I guess I'll have to give you a little overview on how polars work as well. So take a look at this problem, try it out. Don't spend more than 15 minutes on it, but try it out, see what you think, and we'll figure out how to do it on Tuesday, tomorrow. So have a wonderful day, and I will talk to you later. Bye-bye.